Hello again. Let's continue with chapter 4. I hope you're doing well. So let us get started on finish chapter 4, hopefully. We're not going to be able to finish it for this video, maybe next video. All right, so let's get us started here. So what we want to do is to talk about L'Hopital's rule. L'Hopital's rule will make it really easy to take limits. So let's see how it works. First of all, what are the indeterminate forms that we have to use L'Hopital's rule for? These are the list of indeterminate forms. Indeterminate, that means we don't know what they are. They could be, 0, infinity, any number, right? Indeterminate. That doesn't mean does not exist, right? If when we substitute to find the limit and we get one of these, it means that we don't know what the limit is and substitution doesn't work, so we have to use some other method. And this is the method that is pretty useful. Historically, first of all, let me give you some examples. So here we know that x over x to the fifth power, when x approaches 0, is infinity, the limit. Why? Because we know we can cancel one x, and we get 1 over x to the fourth, and the answer is infinity, positive. And x over x is 1, of course, we know because we can cancel the x's and get 1. And then this one, if we cancel x, we get 0. Now notice that if we substitute 0 for x, in all three of them, we get 0 over 0. But look at the answers, are completely different. So three different answers coming from the same structure, 0 over 0. Same is true if we have an infinity limit. So if the x approaches infinity, here we know we can cancel the x's and get 0 because we get 1 over x to the fourth, which is 0. And over here, if we cancel the x's, we get 1 when x approaches infinity. Because this is a constant, so it doesn't really matter, right? So this one, the other one, x to the third over x, is just what? Just x squared, and it goes to infinity. Again, we have three different limits for the same structure. If we substitute, we get infinity over infinity, infinity over infinity, right? So those are two that are for sure indeterminate form, right? Now, here's a little history on 0 to 0. 0 to 0th power was considered to be 1. In fact, in algebra, we assume that is 1. But in calculus, 0 to 0 is indeterminate form. So this guy, Cauchy, in 1821, listed 0 to 0 along with these to be indeterminate form. So we got 1, 2, 3, 4, 5, 6, 7, right? All of these can be converted either to 0 over 0 or infinity over infinity, okay? And in the notes, you can go to Wikipedia link here and read more about it. But these are the indeterminate forms that we're going to talk about, okay? So let's look at the theorem itself. The theorem itself says that f and g are differentiable functions over an open interval containing a, and x approaches a, except possibly at a, right? If the limits are both 0, right? Then, assuming the limits on the right exist, so we assume that this limit exists. If this limit doesn't exist, this theorem doesn't apply, right? And we're going to look at an example where that is actually the case. But for now, if this limit exists, then instead of taking the limit of f over g, we can take the limit of f prime over g prime. That makes it really easy to take derivatives, right? Limits. For example, remember limit of x squared minus 1 over x minus 1 when x approaches 1 is 0 over 0. And remember, before we had to factor something out. Now we don't have to use this theorem. So we say this limit is the same as the limit of derivative. So that's the same as the limit of, what's the derivative of x squared? Plus 1, 2x. Derivative of x minus 1 is 1. So what's the limit when x approaches 1? Is 2, right? It's very easy to find the limits using this theorem. This also works if the limit on the right exists, or if this infinity or negative infinity, if the limit is infinity or negative infinity. This result also holds if you're considering one-sided limits, or if x approaches infinity, negative or positive. All right, so let's prove this. Let's look at an example. I gave you an example already, but let's look at another one. So something like that, we would have to do it this way in chapter before, in previous chapter, chapter 2. Now we could do it this way, and we get the answer, right? When x approaches 2 is 4. Makes sense? You see, take the derivative, take the derivative. Now don't confuse this with the quotient rule, right? We're not talking about quotient rule. We're talking about taking derivative of the numerator and taking derivative of the denominator and then taking the limit. All right, the proof of this is pretty easy, because what we want is this. We want to prove that the limit of f of x over g of x, the limit of f of x over g of x, is the same as the limit of f prime over g prime. So we know the derivative, the definition of f prime is what? Is the limit of f prime at a, right? So it's going to be the limit of, and put a. It's going to be the limit of f of x minus f of a over x minus a when x approaches a, right? And then what is the limit of g prime? Is the limit of, at a again, is f of g of x minus g of a over x minus a again, and then x approaches a. So what we want in the numerator here, we want this to equal to something like this. This has to be in the numerator and this has to be in the denominator. Now in algebra, if you want something, you could just create it by doing what? Created by adding, subtracting, multiplying the stuff, right? So what we want to do here, we want to take this f of x and make it look like that. I want to take g of x and make it look like that, right? So it's easy. First of all, we know that limit of f of x when x approaches a is 0, and limit of g of x when x approaches a is also 0. And so that means, that's how we got here, right? We substituted a for x, and we got 0 over 0. That means f of a and g of a are both 0. That means I can actually subtract f of a from the numerator and subtract g of a from the denominator and get away with it, because they don't change the value of the f of x over g of x. I can also divide the numerator and denominator by x minus a. It doesn't change the value of it, right? And I know the limit of something over something is the limit of something over limit of something, right? Limit of a quotient is the quotient of the limits. And so this turns into this, and I know this is a derivative, right? Right? And I know since f prime and g prime are also continuous, the limit of f prime of x when x approaches a has to be f prime of a. Why? Because f prime and g prime are continuous, right? F and g are differentiable, right? So that means basically we proved what we wanted. And this is the quotient of two limits, which is the limit of two quotient. So we started from here, and we got what we wanted. All right, so here are examples again. It's very easy, just take the derivative, right? When you substitute, you get 0 over 0. So we take the derivative. What's the derivative of x minus a is 1. What's derivative of x squared minus a squared? 2x, because a is a constant, right? So limit of 1 over 2x when x approaches a is just that. Evaluate the limit of 1 minus cosine over x, right? Now remember, we did that using the tricks of multiplying by conjugate and all that. Now we don't have to, because all we have to do is take the derivative. First of all, the L'Hopital's rule applies here because we could take the derivative and we still have a limit. And that limit is 0. So this limit equals to this limit, which is 0. Right? What's the derivative of 1 minus cosine x is 0 minus derivative of cosine is negative sine over derivative of x is 1. So that's sine, and the derivative of sine when x approaches 0 is 0. Okay, the case of infinity over infinity is similar. So if we substitute and we get infinity over infinity, we can also use this theorem, right? And here's an example of infinity over infinity. Now, this would be not easy to do with the previous methods, right? Because when we substitute for infinity for x, we get an e to infinity over infinity. How do we resolve that problem? Well, now we know how. We take the derivative. What's the derivative of e to x? E to x. What's the derivative of x? 1. So this is infinity over 1, which is infinity, right? All right, what's that? Well, again, if you put infinity here, infinity to k would be just a big number, big infinity, and then ln infinity is infinity. Remember, ln looks like this, right? So when x approaches infinity, ln of infinity goes to infinity. And when x approaches 0 from right, it goes to negative infinity, right? All right, so here, ln of infinity, so this is infinity, and this is infinity. So that's what we get. So we take the derivative. Derivative of ln x is 1 over x. Derivative of x to k is k times x to k minus 1, right? And when we substitute infinity here, what do we get? Well, that would be 1 over infinity, which is 0, and this would be infinity. So that's, the denominator doesn't go to 0, but the numerator goes to 0. So the answer is 0. All right? Here's another one. Now, in this one, when you get too excited about L'Hopital's rule, then you keep applying it to everything. Don't do that. First, you have to make sure the L'Hopital's rule actually applies. In this problem, you don't need L'Hopital's rule. You just do the limit, just substitute. When you substitute, you don't get one of these. So it's not L'Hopital's rule. So you just do the limit, 6 over 7. This would be like a trick question on a calculus test. Now here is one that also tricky, because when you try to use L'Hopital's rule, what happens? Well, this happens. You get 1 minus sine over 1. When x approaches infinity, we know sine doesn't have a limit. So this limit doesn't exist, right? But what does that tell us about the limit we want to find? Nothing. It means that L'Hopital's rule does not apply. Don't use it, right? Use some other method. So some other method is easy. So we're going to go and see how we can solve this, right? Why L'Hopital's rule doesn't apply? Because this limit must exist for us to be able to find the limit. And in this case, it does not exist. So how do we do it? Well, we have to use what? We have to divide. This is a common denominator. So we're going to work with operations and see what we can do with this. So x over x is 1. Cosine over x is cosine over x. When x approaches infinity, now this, we can use squeeze theorem, right? On a squeeze theorem, we have seen this before. This is between negative 1 over x and 1 over x. So when x goes to infinity, these two go to 0, right? So that means this goes to 0. So the answer is 1. In the notes, you can click here and watch a video on from MIT. And this guy from MIT works on this limit. Let me show you quickly. I want to make sure the link actually works. Does it go to, looks like it's going to YouTube. Yes. There you go. So it does work. So this is a single variable calculus in that MIT open course. Let me close it. All right, so you can do that on the notes. It's the same problem I just did here. All right, so L'Hopital's rule is very useful for evaluating limits involving the 0 over 0 and infinity over infinity. But what do we do with the rest of them? Well, the idea is to convert them to these two forms. Okay, that's the idea. So let's see. If we have 0 times infinity, right? If f goes to 0 and g goes to infinity, how do we convert it to 0 over 0 or infinity over infinity? Well, it's easy. Keep the 0 in the numerator, and then infinity, make it 1 over infinity, right? So if we have f and g, f times g, just keep the f and make denominator 1 over g. Now this is a complex fraction which is equivalent to that, right? Because this complex fraction, f times something, a number times a number is the same as the number divided by the reciprocal, right? So now what does that do? Well, that makes it 0 over 0. Or you can keep the infinity in the numerator, so keep the g in the numerator and make the f go 1 over f go in the denominator, right? Now you have infinity over infinity because 1 over 0 is infinity. Either way, you can convert 0 times infinity to 0 over 0 or infinity over infinity. You can stick to one of them and continue with that. Okay, here's an example. We got limit of 1 minus x times tangent pi over 2 times x when x approaches 1 from left. Now, obviously, if you substitute, you get what? 0 times tangent. Now, tangent looks like this, right? It's got, so tangent looks like this. So this is pi over 2 here. So when x approaches 1 from left, right? So here's 1, you're approaching it from, so 0.9, 0.95 something, approaching 1, that means you're approaching pi over 2, right? From left of it, right? So you're approaching pi over 2 from left of it. Because x is what? Smaller than 1. So you're multiplying something is smaller than 1 times pi over 2 and make it smaller. And as you increase it to 1, you approach pi over 2 and looks like the function goes to infinity, right? So we got 0 times infinity. All right, so we accomplished that. So we know that this is this form. Now all we have to do is decide which one you want to keep in the numerator. Let's put the 0 in the numerator. Remember, this is f, this is g, right? So we keep the f, which is that, in the numerator, and then 1 over this goes in the denominator. And we know 1 over tangent is cotangent, right? So this is the same, and this would be 0 over 0, right? Now we take the derivative. What's the derivative of 1 minus x? Negative 1. What's the derivative of cotangent something? Negative cosecant squared of something times derivative of something, which is pi over 2. And now, if we substitute 1, well, what is cosecant squared of pi over 2 times 1? Well, that's just pi over 2, which is the same as 1 divided by sine of squared of pi over 2. And sine squared of pi over 1 Sine of pi over 2 is 1, and the squared is just 1. So 1. So this would be 1, so that's negative, and the negative cancel each other. So what is 1 divided by pi over 2? Well, it's 2 over pi. So that's the limit of this one. Make sure you understand this process. Maybe you can stop the video and do it yourself once. So let's move on to another one. What do we do with infinity minus infinity? Well, that's another indeterminate form. Well, what we can do is we can create 0 over 0 with this trick here. So what we start with is f minus g. So this trick will work. So what do we do? Multiply it by fg and divide by fg. Doesn't change anything, right? And then separate these into two reciprocals, right? So this divided by this is the same as f minus g over f over g divided by 1 over f over g, right? You see, if you write this complex fraction in this form, right, you get the same thing, right? Now we separate f over f of fg minus g over fg, right? F over fg, right, minus g over fg, and here the f gets cancelled, so you get 1 over g, and here the g's cancel, so you get 1 over f. And this is just 1 over fg. Now, why do we do that? Because remember, both of these are infinities. So what happens here? Well, we get what? We get 0 minus 0 over 0, shows 0, 0, 0 over 0. So we have 0 over 0, and we accomplish what we wanted. So whenever we have a problem like this, we use this formula, right? So let's do that. So we have 1 over x squared minus 1 over tangent x, infinity minus infinity. When x approaches 0, that would be infinity. Tangent 0 is 0, so 1 over 0 is infinity. So what do we do? Remember, this is our f, this is our g. So we use this formula, 1 over g minus 1 over f divided by 1 over f times g. That's exactly what this is. Now, this automatically would be 0 over 0, right? Because we just did it here. So what do we do? Simplify this before you take the derivative. So we simplify this. This is 1 over x squared. So in the denominator, we just have x squared tangent x, right? That's the denominator here. And the numerator, we can, 1 over this is what? Is tangent x, right? And 1 over x squared is just x squared, right? So that's what we are going to get. And so this is actually so the denominator. So let me do this actually. So let me write it. So 1 over so this one right here would be, denominator is 1 over oops, 1 over x squared tangent x, right? So that's just, that's just x squared tangent x in the denominator. And this one right here is going to be, if you combine these two, you get tangent x minus x squared. If you want to subtract these, right? So let's see, what do we get? We get 1 over tangent x, and then 1 over x squared minus, which is tangent x minus x squared, right? All right. It wasn't that difficult, actually. So take the derivative. So secant squared minus 2x, derivative of that. Now remember, this is a product rule. because it's a product. So we have to use the product rule to take the denominator of this one. So derivative of x squared is 2x times tangent plus derivative of tangent, which is secant squared, times x squared, right? Again, don't confuse this with the quotient rule. We're just taking the derivative of numerator and taking derivative of denominator, right? Okay, so that's what we get, and then we just substitute. Now we substitute, we actually get an answer, because this x, if you substitute 0 here and 0 here, and this is just 0, so denominator goes to 0, right? And the numerator, what is secant of 0? Secant is 1 over cosine. Cosine is 1, so that's 1 over 1. So that's 1. 1 minus 0, right? So that's 1. So it's 1 over 0, and since you're approaching 0 from right, this would be, of course, positive infinity, right? You're approaching 0 from right, this would be a positive infinity. All right. All right, so let's look at the other three forms, right? So we talked about 0 over 0, we talked about infinity over infinity, we talked about 0 times infinity, we talked about infinity minus infinity. What do we do with the other three, right? And the answer is, we are going to assume that we have y equals to f to the g power, right? And we're going to take ln of both sides to bring the g of x downstairs, right? You see that? And then once we do that, we take the limit of ln y. That means we take a limit of this. And then we convert it to what? 0 over 0, or just 0 over 0. Maybe stick to that one. Now, what happens if you do this? Well, if you take the limit of g of x times ln f of x, if we have this case, that means f is 0 and g is 0. So what we get 0, and then ln 0 is infinity, so we get 0 times infinity, right? Which is right there. Now, if we have the second type, that means f is 1, right? And g is 0, then what do we get? Is 0 times ln 1, f is 1 and g is 0, right? And g is infinity, right? F is 1 and g is infinity, right here, okay? So what do we get here? Well, we get infinity times ln 1, which is 0. Again, we get the same form. And what if we have the third type, which f is infinity and g is 0? Well, again, we get ln infinity, which is infinity, and then g is 0. 0 times infinity again. Okay, so now we are going to find formulas to convert these to what? To 0 over 0. So if we have 0 to 0, right, we'll end up with this. And we can keep one of them in the, we have 0, they're both 0. So we keep one of them in the numerator, the other one 1 over ln f of x gives you 0 over 0, right? If this is 0 and this is 0, we get 0 over 1 over ln 0, which is infinity. 1 over infinity is 0. And if f is infinity and g is 0, then again we get 0. And ln infinity is infinity, 1 over infinity is 0. And if f is 1 and g is infinity, ln infinity, right? So ln 1 is 0 because f is what? F is 1, right? So that's 0. And then 1 over g is infinity, so that's 0. So in either case, we get a structure that we can take the limit of. Once we do this, then we take the limit. But remember, this is not the limit of what we started with, y. This is the limit of ln y. So once we have the answer out of this, whatever the answer is, we have to do what? We have to have e to that to find the limit of ln y. The reason, the ln limit of y. The reason is that we get something like this. Limit of ln y equals to, let's say, some number, right? So we know we can put the limit inside, so that would be the ln of limit of y equals to that number. And how do we get rid of the ln? To find limit y, we do e to both sides, right? So out of the left side, we get y, limit of y, equals to e to that number, right? So always the answer would be e to whatever the answer is that we find here, right? So that's the idea. I'm going to do one of each. So here is an example of 1 to infinity. When x approaches 0, this is 1, 2, cotangent of 0 goes to infinity. Remember, cotangent looks like what? Cotangent looks like kind of this. Goes to infinity this way and this way. So when you approach 0 from right, the cotangent goes to infinity. That's infinity, and so 1 to infinity. We don't know what the limit is, so we're going to take the ln of both sides and write it like this, and take the limit of this. And we know how to do that. We have a formula for it. So ln of ln f of x over 1 over g of x. So what is ln of, what is f of x? F of x is that, and g of x is that. So it would be ln 1 plus x over 1 over g of x, which is that, because 1 over cotangent is tangent. Okay, now we take the derivative. What's the derivative of that? 1 over that. What's the derivative of this? Secant squared. Now, we could simplify. You don't have to, still 1. But it's easier to work with cosine. So secant squared of 0 is 1 over cosine squared. And the answer is, this is 1 over 1, which is 1. Now, is this the answer to this limit? No. This is the answer to this limit, right? Limit of that. So what do you have to go through to find the answer to that limit? We have to basically take e to that power, which is e to first power. So the answer is e. Okay? And I have the explanation again over here, why. Let's do another example. What about this one? Well, x approaches 0, so that would be 0 to 0, right? When you substitute, you get 0 to 0. So what do? Well, we take ln of both sides again. We take the limit of this. And again, remember, this is f, right? This is f, this is g, right? So what do? Well, we're going to use that formula for 0 to 0. Is g of x over 1 over ln f of x. So what is our g of x? Is sine. What is our f of x? Is x. So it would be sine x over 1 over ln of f, which is x. Okay, now this is the same as ln x over 1 over sine x, right? You can switch them. And when x approaches 0, that's the same as cosecant, right? So that's what we get. Now this is now infinity over infinity, right? In this case, I converted it to infinity over infinity, right? So that's another way, another way to convert it. As I stick to 0 over 0, it looks like I lied. So no, this is infinity over infinity, okay? So it was 0 over 0, right? This was 0 over 0, but since we took the reciprocal of each, we took it to be infinity over infinity. That's the same thing. Well, this is 0 over 0, right? Right here. Sine of 0 over 1 over ln 0, right? So, so we can use infinity over infinity is okay, right? All right. So all right. So what do we do with this? Well, we're going to take the derivative of numerator and derivative of denominator, just like we did before, and we end up with what? When this approaches, so what do we get? We get, if you simplify this x goes in the denominator, and then we have -1, there's a negative here, -1 over this, right? And now, what do we do? Well, does it work? What do we do here? Well, we can use this structure here. So we write x times 1 over sine, and then we make cotangent cosine over sine, right? And then we can simplify this, so that would be sine squared, and the numerator would be x times cosine x, right? So think of a complex fraction like that. So it would be sine x times sine x in the numerator. Let me give you a rule here. So if you have something like this, you can write it as AD over BC, right? Complex fraction. So -1 times this over 1 times that, which is x times cosine x. All right, and this right here, we can separate it into sine over x and sine over cosine, right? And we end up with 0. Thus, ln of limit of ln of y is 0. So that means the answer that we want is e to 0th power, right? If the answer to the limit was 0, then the answer to the original limit would be e to 0, which is 1. All right? Okay, so so again, we converted 0 over 0 to infinity over infinity by this trick, right? All right. This, there are some other ways probably to do this. You can stop the video and see you can actually use the original 0 over 0 and do it, okay? So that's just one way to do it. All right. Other intermediate value theorem, again, is the third one, which is infinity to 0. When x approaches pi over 2 from left, again, remember tangent looks like what? Tangent looks like this, right? So when x approaches pi over 2, right, from left, so again, we have another one here, and that one also looks like what? Looks like that, right? So when you approach pi over 2 from left, this goes to infinity, right? So that would be infinity, and cosine 0, cosine pi over 2 is 0, so infinity to 0. So when we substitute, that's what we get. Okay, so what do? We use this formula again. So y equals to tangent to cosine x. Then we take ln of both sides, so we take the derivative of this. And again, this is f, this is g, right? So we're going to do g here over 1 over ln of f. And this would be 0 over 0 automatically. So that would be limit of, if you write it in this form, just again, this is cosine over 1 over ln tangent, right? So would be ln tangent over secant. You know, instead of writing cosine, we write secant, right? That's the same thing. So basically, let me see. So you get cosine x times ln tangent x, right, over 1. And instead of cosine, we could just write 1 over what? 1 over secant. And we get this, right? All right, now we could take the derivative. So what's the derivative of ln something? is 1 over something, 1 over tangent, times the derivative of tangent because secant squared. And what's the derivative of secant is secant tangent. And now we simplify it, it would be secant over tangent squared, right? You can write it, just the algebra, secant is squared over tangent times, this is this over 1, so it would be 1 over what? Secant tangent. And now one of these secants actually cancels one of these, right? So oops, go back. So you end up with 1 secant, right, over tangent squared, right? All right, now what is the limit? Well, it looks like we end up again with what? When we substitute, we have pi over 2 here. Secant pi over 2 is 1 over cosine pi over 2, right? And again, we get the same problems, infinity over infinity, right? This time we get infinity over infinity, and it's okay. We can use the L'Hopital's rule one more time. Take the derivative again. Secant tangent, derivative of tangent squared is 2 tangent x secant squared. And now again, the tangents go away, one of the secants go away, we get this. This limit does exist, right? Instead of 1 over secant, we could just put cosine, right? And that's just 1/2 cosine when x approaches pi over 2, which is 0. Now that's not the answer. E to that is the answer, right? The answer to this is e to 0, which is 1. Again, stop the video and make sure you can get this yourself. And we're going to talk about this idea of growth rates. Now the growth rates have to do with ratio of two functions. So if you have a ratio of two functions, let's say f of x over g of x, and both of these go to infinity, then we use the L'Hopital's rule to find the limit. And if the limit is 0, we say that the denominator grows much faster than the numerator. That's how, when x approaches infinity, this fraction goes to 0. The reason is that g of x grows faster, much faster than f of x. So fast that eventually this fraction actually goes to 0. That means g of x becomes so big compared to f that we can assume this ratio is 0. Now, if g of x over f of x goes to infinity, well, that means what? That means, again, g of x grows much faster than f of x. So eventually, f of x doesn't even matter. It's not 0, but it's so small, right, compared to g of x, that the ratio would go to infinity. All right? And if the limit is not 0 or infinity, but it's some kind of number between 0 and infinity, then we say that f of x and g of x grow at comparable rate, right? That means one of them doesn't get so much bigger than the other one that is going to affect the ratio, go to 0 or infinity. So the ratio still stays some number. As x goes to infinity, it neither goes to 0 nor to infinity. It just goes to what? Some number. So in this case, we say that the two functions grow at comparable rates. So let's look at some examples. Here's an obvious example that which one grows faster, e to x or x squared? Well, let's see. Take the limit. What is the limit? Well, we don't know. We have to take we have to apply the L'Hopital's rule. What's the derivative of e to x? E to x. Derivative of 2x. Derivative of x squared, 2x. So we still get infinity over infinity. So we do it again. E to x, 2. Now we get infinity over 2, which is infinity. What does that mean? it means that e to x grows much, much faster than x squared. And you see the picture here. So x squared grows much faster than x. E to x grows much faster than this, right? All right, let's look at another example. What about ln x compared to x squared? Now here's x squared going to infinity, here's ln x going to infinity. Obviously, looks like ln x is not catching up, right? So what do? We take the derivative again, 1 over x over 2x, which is 1 over 2x squared, and when x goes to infinity, that's 0. What does that mean? That means the denominator grows much faster than the numerator. So in this case, it goes to infinity, the ratio goes to 0. Okay? Now what about this one? X to 100 over 3 to x. Again, we get infinity over infinity. But this one, the calculations, the numbers are so huge that don't try this on your home calculator. It's not going to work. But if you use a computer and maybe Wolfram Alpha online, you can actually see that 3 to x actually grows faster. Now, how can we prove that? Well, we take the derivative. Okay, what's the derivative of that? 100 times x to 99. What's the derivative of 3 to x? It's 3 to x times ln 3, right? Well, that doesn't work because you still get infinity over infinity. Well, we keep doing it. How many times? Well, as many as possible, as many as we need to get rid of x in the numerator. And notice that what we're going to get. We get 100 here, then we get 100 times 99, and continue this way, right? So if we continue taking derivatives, this is the same one, I just repeated it. But the next one would be what? Would be 100 times 99 times x to 98, right? And then what we're going to have? We're going to have another 3x. It would be 3 to x, right, to second power, and would be ln 3 to the second power, and so forth. And if we keep doing that, eventually what you get is 100 times 99 times 98 times 97, all the way to 1. So that's actually 100 factorial. And you get 3 to x to 100 and ln 3 to 100. Now we see the limit is 0. That means, again, this grows faster. But that grows faster eventually. That means we're going to have to calculate these numbers for a long time. So if you put this in calculator, there is no way with your calculator that you're going to get the intersection that they have way over here. So these two graphs intersect at 3 points. At this point, which is to the left of 0, they intersect. They intersect at 1. And then they're going to intersect way over there, at x equals to 579 point something. Okay? So as you see over here, before you get to, 579, it looks like, that x to 100 is much bigger than 3 to x. But look at here. When you get to 646, 3 to 646 is this huge number, which you can't even calculate with calculator. It's so huge. You have to use computer program. And I use GeoGebra. And I'm going to show you what I did in Wolfram Alpha. So 646, so this is 3 to x, when x is what? 646. And then this is what? This is x to 100, when x is 646. And notice the number. 3 to x, it has a whole lot more zeros than this, right? So it's much, 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 much bigger than this. At 579, they're the same. And I'm going to show you the answer from Wolfram Alpha. It gives me 3 answers. Notice that Wolfram Alpha estimates, so this is really 1, right? And look at this number. So they intersect over here, they intersect over here, they intersect way over there. You can't even see in Wolfram alpha, right? So you have to move this. And if I do that, these things are so close you can't even see two of them. So it's a long, long, long way over there that they intersect again. And then the red one, so basically it catches up. So the red one, well, that doesn't look good, but the red one is going to go that way, and the blue one is going to be like that. That would be red and blue. Eventually. Okay? When? After 579. So this point of intersection again happens when x is 579, somewhere around way over here, way over there. Okay, these are, this is not 500. I mean, the y value, we don't have, we don't have the y value because it would be way over there, right? For the blue one, we don't have the y value. And for the red one, we don't have the y value of 579, right? It's way over there. Okay, so I have here this idea. So we know that 3 to x even goes faster than x to 100. All right, so in the next video, I'm going to talk about Newton's method, okay? So I'm going to stop here and stop this video. I hope it's not too long, okay? So I'm going to see you in the next video, okay? Take care of yourself and others.